Hello everyone. The title of this video is Solving Compound Inequalities with the word OR as the connecting word, as opposed to AND. Alright, I'm going over 14 examples, and as with other videos, I would like you to try to work on the problems I'm doing in the videos. Try to work on them before you see me do them. See how you're doing, how much of the material you grasp yourself. And also you can navigate through the examples pretty quickly by looking at, I have the timestamps for each example in the description of the video. Pardon me. Alright, each of these examples I'm going to go over in this video are taken directly from a free online textbook at openstacks.org. This textbook is their Intermediate Algebra 2nd edition, and it's from section 2.6 on solving compound inequalities. Alright, and what I'm going to the exercises you'll see in this video are the exercises 402 pardon me 402 through 415. Alright, and so in my video here, example 1 will correspond to number 402, and example 14 will correspond to number 415, and so on. Right? So if you want to take a look at a specific example, count down how many there would be, and then look for that example number in my video in the timestamps. Okay, so let's get to it. Pull up the piece of paper here with the first example. And in each of these examples, I'm asked to solve the compound inequality, graph the solutions, on a number line, and write the solution in what's called, interval notation. Alright, so the first one here is, again, two inequalities connected by a connecting word, either and or. That's called a compound inequality. And every single example in this video, the connecting word is the word or. So the first one here is x is less than or equal to -2 or x is greater than 3. So off to the side here, I'm going to write the steps down to finding the solutions of of a compound inequality like this. So first you solve each equality separately, or solve each inequality in the compound inequality, which is already done. Here both of these are already solved, right? The variable is alone on its own side, and I prefer having it alone on the left side, but whatever you like. So that step's already done. Then what I'm going to do off to the side is make a rough graph. Alright, not a final graph. Make a rough graph of both inequalities on the same number line. So the numbers that satisfy this one or this one. So I'm going to do this on the same number line. Alright, and then for the final graph, right, this is I'm going to make a rough graph and then a final graph. Now the numbers that belong in the final graph, right, the solutions to a compound inequality where the word or is the connector. When you see the word or, this means that numbers, or I'll say solutions, solutions are numbers that satisfy either inequality, either the first one or the second one, or both. Right? So solutions are any numbers that satisfy at least one of the inequalities. All right, at least one of the inequalities. So either the left one or the right one, or both. All right, so this is very, very loose, very, very inviting to lots of numbers being solutions of the compound inequality. Okay. And the numbers that satisfy at least one of these belong on my final graph. All right, and then I'll talk about writing interval notation as well. All right, so the first is going to be my rough graph. So there's a number line. Now the numbers mentioned here are -2 and +3. Just make sure you're marking those off in the proper places. You know, -2 would be to the left of +3 on the number line. And then I'll graph each of these, one on top and one on bottom. I like doing one on top and one on bottom. You can do both of them on the same side of the number line. I don't really care. So first are the numbers that are, I want to graph the numbers that are less than or equal to -2. So I'll do that on top here. So that's all these numbers that are less than -2 or equal to -2. So a little bracket there or a closed point to indicate that -2 is part of that. Then I'll also graph the other set of numbers, right? The other inequality. The values of x that are greater than 3. I'll do that below. That's these numbers here. The values of x greater than 3 are 4, 5, 6, to the right of 3. But not including 3, right? So parentheses on 3 or an open point on 3, a hole. And then I just simply make stock of what are the solutions of the compound inequality, the whole thing. What would make this a true statement? What values of x? Remember, the word or is very lenient, right? Very, very loose. All these numbers that I graphed make the first inequality true. So they make the whole thing true. Right, this or inequality, this or compound inequality. So these are solutions of the compound inequality. And so are these. These numbers greater than 3, these satisfy the second inequality. So when I plug in 4, yeah, 4 is not less than or equal to -2, but it is greater than 3. So either this or this is true, making the whole statement true. All right. So the or means, either this is true or this is true or both are true. It's sometimes referred to as the inclusive or. But then these are solutions as well. Then these are solutions also to my compound inequality. So every single one of these numbers belongs to my final graph. Every single one of these numbers belongs to my final graph. All right, so the final graph, which is going to be a number line where I mark off all the solutions to the compound inequality, every number that satisfies this or statement. It's just all these numbers here. Right? All the numbers less than or equal to -2. Right? All the numbers left of -2, including -2. Basically, I'm just drawing these again, but on top, right? So that they're part of the same graph. And all the numbers greater than 3, but not equal to 3. All right, I'll bubble this in. Here's the final graph. All right. Now, for interval notation, there's a break. See how there's a gap in the graph? So there are technically, 2 pieces. So there are 2 intervals, right? When you're doing interval notation, you make an interval for each piece. For each piece of the graph. And you always draw these intervals, remember, from left to right. So the first piece, going from left to right, well, there is no far left end, right? So that would be from negative infinity up to negative 2. So I put negative infinity, comma, negative 2. Remember, there's always parentheses on the infinities because, infinity or negative infinity, those are not numbers, so they can't be solutions. Negative 2, though, is a solution of our compound inequality, so I put a rectangular bracket on that. And then to indicate that there's a gap, to indicate that there's a separate piece, we're going to put a symbol basically for the word or, a set notation symbol called the union symbol. All right. So yeah, this is called the union symbol. And it's basically set notation symbol for the word or. Again, just to indicate that there's a gap, a break in the intervals. So I have this set of numbers less than or equal to negative 2 are solutions, or, and this other interval also contains solutions. The interval from 3 to positive infinity. Right, from 3, again, always going left to right. 3 to positive infinity. 3 is not a solution of this statement. No, it doesn't make it true, so I put parentheses on the 3. And infinity is not a number, right? Always parentheses on the infinities. And then here is what they would call the interval notation describing the solutions of this compound inequality. Right? All the numbers less than or equal to negative 2 are solutions, or all the numbers greater than 3 are also solutions. And don't forget when there's a gap, when there's a separation in the intervals, use this union symbol. You're going to see that often is just, again, just a symbol for the word or. Okay, wonderful. And that's it. All right. And be careful. Don't connect these. Very often people want to connect inequalities. So I'll say this off to the side here. Don't connect or inequalities. Because they won't make sense. All right, and if you saw my video on the and inequalities, you saw when is the only scenario in which you can make a connected inequality is when there are solutions between two numbers. Here the solutions aren't between negative 2 and 3. But you see, people might want to try this. They're like, oh, I see the x in both of these, so I'll write x in the middle. And x is, less than or equal to 2, negative 2, and then x is greater than 3. And people want to write that. Putting both of these together as one. Don't do this, especially with these or inequalities. This doesn't make any sense. All right, this here is nonsense. Because look at what it implies. It implies that 3 is less than negative 2. That doesn't make any sense at all. That is totally nonsensical, meaningless. All right. And that's going to happen if you try connecting these or inequalities. So please don't do it. All right. Just leave them separated by this word or. Okay. All right. So let me get to the next example. Again, these first few examples I have are pretty easy to start because the inequalities are already solved. Okay, so you see here I've got x is less than or equal to negative 4, or x is greater than negative 3. And they're already solved, right? The variable is already alone on one side of each of these inequalities. So now for the solutions of the compound inequality, or the whole thing, we're looking for numbers that I can replace x with to make either this inequality true or this inequality true, or both. Right? So Off to the side, I'll make a little rough graph, right? The numbers -4 and -3 are mentioned, and don't forget, be careful with negatives, right? -4 should be to the left of -3. These numbers, x is less than or equal to -4, are the numbers to the left of -4, including -4. The numbers greater than -3 are these numbers, right, with parentheses on -3 there. And again, basically any numbers you draw are going to be solutions to an OR inequality, right? All these numbers here satisfy the first inequality, therefore making the compound inequality true. All these numbers here to the right of -3 make the second inequality true, and therefore make the entire compound statement true. Alright, so the final graph, again you have -4 and -3 mentioned. All the numbers less than or equal to -4 are solutions of the compound inequality. All the numbers greater than -3 are also solutions of the compound inequality. There's your final graph. And then when I go to put in, my interval, the interval notation for this set of solutions, again notice that there is a break, there's a gap in this picture. So there are two intervals I need to write in interval notation, and connect them by the word or that union symbol, as in the first example. So going from left to right, this first piece we have from -infinity up to -4. Always parentheses on the infinities and a bracket on -4. Right? That is a solution of this compound inequality. Then that's in union with, right? Again, this is like OR. And then the numbers from -3 to positive infinity for this second interval, this second piece of the graph. And parentheses on -3, parentheses on infinity always, because again, -3 is not a solution, infinity is not a number. All right, and here's your interval notation for the set of solutions. And pretty simple, I feel, especially in the beginning here where the inequalities are already solved for. Okay, so yet again, I have an example where x is solved for in both of them, and we have x is less than 2 or x is greater than or equal to 5. So again, off to the side, the numbers 2 and 5 are mentioned. I'm going to make a rough sketch, rough graph. First I'll label all the numbers that are less than 2. I'll do that up top. That's those numbers. All the numbers that are greater than or equal to 5 I'll do below. That's these numbers. Right? And again, basically whatever numbers you draw in your picture here in the rough graph will be in the final graph as well. Right? Because all these numbers to the left of 2 satisfy the first inequality, therefore they satisfy the compound inequality. Right? That's how loose the OR inequalities are. And all these numbers here that I labeled, greater than or equal to 5, they satisfy the second inequality, so therefore they satisfy the entire compound inequality with that word OR there. Alright, so the final graph, the one I would hand in if this were an assignment, would be the following, right? All the numbers less than 2 but not including 2, right, are solutions of the compound inequality. All the numbers greater than 5 and 5 itself, right, so bracket or a close point on 5, those are also solutions of this compound OR inequality. And then the interval notation, again, two separate pieces here, so I'm going to break them up with that union symbol. Right? First piece goes from -infinity up to +2, parentheses on both of those, right, because again 2 is not a solution. In union with, right, and then the other set of solutions is from 5 to +infinity, bracket on 5, since 5 is a solution of the compound inequality, and parentheses on the infinity. Right? There's the interval notation for that set of solutions. All right, great. Alright, I got one more of these where it's already solved for. Alright, where both inequalities are already solved. Here's example 4. So we have x is less than 0 or x is greater than or equal to 4. Alright. So again, off to the side, a rough graph. 0 is mentioned, 4 is mentioned. All the numbers less than 0 are these numbers. All the numbers greater than or equal to 4 are these numbers. I'm going to put them on the bottom. And again, this is an OR inequality. So any numbers that satisfy the first inequality or the second inequality or both belong to the final graph. They are solutions of the compound inequality. So all these numbers here, they satisfy the first inequality, so they're good. All these numbers here satisfy the second inequality, so they're also part of the solution set. So my final graph, right, the one I would hand in, is this. Right? All the numbers less than 0, but not 0 itself, or all the numbers greater than 4 or equal to 4. And there's your final graph, right? A picture of all the numbers that would satisfy this compound statement. Then interval notation. Again, there's a break in the graph. There are two separate pieces, so yet again I'm going to be drawing two intervals connected with that OR symbol, the union symbol. This first interval, you're going left to right here from -infinity up to 0. And parentheses on both of those, because again, 0 is not a solution of the compound inequality. In union with, right, the little union symbol. And then the second piece is from 4 to positive infinity. With the bracket on 4, rectangle, 4 is a solution, and a parenthesis on infinity. Right, there you go. Interval notation. Alright. So now in the next example, we have, some inequalities that we need to solve. Now, I'm going to be assuming here that you've seen either some other videos of mine or you already know how to solve inequalities in multiple steps. So what I'm going to do is I'm just going to say the steps that I performed in my head and write the final result. I might write some intermittent steps here and there, but I'm not going to write out every little thing I'm doing. Alright, I'll leave that to you. So the first inequality here, 2 plus 3x is less than or equal to 4. First I would subtract 2, right, giving me 2 on the right side, and then divide by positive 3, giving me 2/3 on the right side. Alright, so and at no point did I multiply or divide by a negative number, so the inequality symbol does not flip. So the numbers that satisfy this first inequality are the numbers less than 2/3 or 2/3 itself. And then we have the OR, and then same thing over here. First I would subtract 5, and that would give me -6 on the right. And then I would divide by -2. Dividing by -2 would flip the symbol. Right, change the direction of the inequality. So instead of is less than or equal to, it's is greater than or equal to. And I'd have again -6 divided by -2 would be +3. So I've solved both inequalities, so I'll circle that. Here's a description of all the solutions of this compound statement. And off to the side, a nice rough graph. Now 2/3 and 3 are mentioned. Right, 2/3 and +3 would be to the right of that, and less than or equal to 2/3, that's these numbers. Greater than or equal to 3, that's these numbers, and yeah, it's an OR compound inequality. So all these numbers, right, they satisfy the first one, so they're solutions of the compound inequality. And all these numbers satisfy the second inequality, so they're solutions of the compound inequality, right? So the final graph is just basically these two again. Now, if you don't want to draw them again, you can always jump to the if you see what the final graph is going to look like right away, you don't have to draw a rough graph. Right? I just like doing a rough graph. Right? If you see what the final graph is going to look like in your head, just draw it. All right. So here's the final graph, what I would hand in if this were an assignment. Right? All the numbers less than or equal to 2/3 are solutions of the compound inequality. All the numbers greater than or equal to 3 are also solutions of this compound inequality. Right, so there are the solutions, there's the graph, and then interval notation, again, break it. There's a gap in the graph, a break in these intervals, so I need two of them. First one's from negative infinity to positive 2/3, parentheses on the negative infinity, bracket on the 2/3. Then the union symbol, right, to indicate the gap, indicate the or, right? And then the second interval goes from 3 to positive infinity. Bracket on the 3, parentheses on the infinity. Right? There's your interval notation for this solution set. Okay, so hopefully so far so good. Right. Next example, pretty similar. Some ones I have to solve first, and then they're connected by the word or. Alright, so just as before, I'm going to just describe what I'm doing for the most part. I might write some intermittent steps here and there, but I'm not going to write down every little thing. I'll leave that to you. So this one I would subtract the 4, and it would give me -6 on the right. And then dividing by -3 would give me +2 on the right, and flip the symbol because I divided by -3. So less than or equal to becomes is greater than or equal to. Alright, so the numbers that satisfy that first inequality are the numbers greater than or equal to 2. Or, and here I would add 1, giving me -4 on the right. Divided by 2 would be -2 on the right. And the inequality symbol would not change because I didn't divide by a negative, right? Didn't multiply or divide by a negative number. Alright, so here's the solutions described in this compound inequality. I circle that. Make a quick rough sketch over here. The numbers mentioned are -2 and +2 here. Numbers greater than or equal to 2 are these numbers. Numbers less than or equal to -2 are these numbers. And any number you draw, any number that shows up, satisfies at least one of these, so it satisfies the entire or statement, the entire compound inequality. So the final graph contains the numbers, less than or equal to -2, also contains the numbers greater than or equal to +2. Right, and there you go. There's a picture of all the numbers that satisfy the compound inequality. And then just as the previous several examples, the first 5, there's a break in this, right? There's a gap. So we have 2 intervals to draw, and then connect them with the union symbol representing or. First interval from left to right there is from negative infinity to -2. Always parentheses on the infinities, and then I got a bracket there on -2 because it is a solution. Then to represent kind of the gap here, we got the union symbol, right, or, and then these other numbers are solutions, from +2 to positive infinity. Bracket on 2 since it also is a solution, and parentheses on infinities all the time. And there's your interval notation. Okay. So next one, again, you got a couple inequalities to solve, and again connected by the word or. First step, on this one I divide by 2. I would change the right side to 2. Then I would add 1, making it 3. Then divide by 3, making it 1. And you still have is less than, because at no point did I multiply or divide by a negative number. So I have x is less than 1, or And this one I'd add 5, giving me 6 on the right side. Dividing by 3 would give me 2 on the right side. And you still have is greater than, because again, at no point did I multiply or divide by a negative number. So here's a description of the solutions, right? Again, quick rough graph over here. 1 and 2 are mentioned. X is less than 1, that's these numbers. X is greater than 2, that's these numbers. And again, any number I draw here, since this is an OR statement, any number I put on this rough graph is going to also belong to the final graph. It will satisfy the compound inequality. So the final graph got 1, got 2, and all the numbers less than 1, but not including 1, are solutions of the compound inequality. And all the numbers greater than 2, but not 2 itself, right? So parentheses on that are solutions of the compound inequality. Make at least one of these true. Then just as the first 6 examples, you got a break here, 2 separate intervals. So I'm going to draw 2 intervals, with that union symbol between them. Left to right, you got from first interval there is from negative infinity up to positive 1, and parentheses on both of those. In union with, right, or, and then this other set of solutions is from 2 to positive infinity, parentheses on those as well, right, because 2 is not a solution and infinity is not a number. Great. All right, next. All right, number 8, example 8. Now here, because 3 doesn't go into 5 evenly, I'm going to actually distribute first. We'll have 6x minus 9 after distributing the 3 is less than negative 5. Okay, and then I would add 9, giving me 4, and then divide by 6. So x is less than 4 divided by 6, but that would reduce to 2/3, right? 4/6 is the same as 2/3. So there's the numbers that satisfy the first inequality. And if they satisfy the first inequality, they are solutions of the whole compound statement, right? Because of the word or. This one I'm adding 1, giving me 4 on the right side, then dividing by 4, giving me 1 on the right side. And again, the inequality symbol wouldn't change since I never multiply or divide by a negative number. Alright, and making a rough sketch over here. Now you got 2/3 and the number 1. X is less than 2/3, that's these numbers. X is greater than 1, it's these numbers. So all these numbers belong to the final graph, all these numbers belong, they're satisfying the compound inequality. So here we do have the solutions. And my final graph, you got 2/3, you got 1, and all the numbers less than 2/3 are solutions, but not 2/3 itself. All the numbers greater than 1 are solutions, but not 1 itself. There's your final graph. And then the interval notation, as in the first 7 examples, there's a break in the graph here, there's a gap. So I'm going to be writing 2 intervals connected by that union symbol for the word or. First interval, left to right, negative infinity up to positive 2/3, parentheses on those. Union for the gap, right? Union for the word or. And then second interval, left to right, is from 1 to infinity, parentheses on those. Right? They're not solutions. Okay. Example 9. Right, kind of flying along here. I'd add 2 to get 6, and then to get rid of 3/4 I'd multiply by 4/3, and 4/3 times 6 would be 8. So x is greater than 8 are the solutions of that first inequality. And since this is another or statement, all the numbers greater than 8 are also solutions of the whole compound inequality. Then this one, dividing by 4 just keeps 0 over here. And then I could just simply add x and look at it the other way. We'd have x is less than 2. Right? Or you could subtract 2, get negative 2, divide by negative 1, and flip the symbol. Get x is less than positive 2. Either way you do it. Alright, and again, rough graph here. 2 is mentioned. 8 is mentioned. X is greater than 8. That's these numbers. X is less than 2. It's these numbers. Again, just as in the previous 8 examples, any number I drew on this rough graph over here is a solution because, again, it's an OR statement. Any number that satisfies either inequality is a solution of the compound inequality. So we have our solutions described here. The final graph, the one I would hand in, 2 and 8 are mentioned, and all the numbers less than 2 are solutions, but not 2 itself. All the numbers greater than 8 are solutions, but not 8 itself. And just as in the previous 8 examples, you have the 2 intervals here with a gap. First interval is from negative infinity to 2, with parentheses on those ends. Union symbol for the gap, right? The word OR, basically. And then the other part of the set of solutions is from 8 to infinity, right? 8 to infinity going left to right, and parentheses on those as well. Okay, moving right along. All right. Example 10. Same procedure, right? Solving these inequalities and noting that they're connected by the word or instead of the word and. Alright, so here, this one I would add 3, giving me 8 on the right side, and then multiply by 3 halves. Now 8 times 3 halves is 12. So we have x is greater than 12, right? Notice the symbol doesn't change because I never multiplied or divided by a negative. Or, here I can get rid of the 3 pretty easily. Divide by 3, you got 2 on this side. Subtract the 5, you'd have negative 3. Then multiply by negative 1, you'd have positive 3. But the symbol would flip. Instead of greater than, it'd be less than. Alright, so numbers less than 3 satisfy that second inequality. And making a rough sketch over here, the numbers 3 and 12 come up. X is greater than 12, that's these numbers to the right of 12. X is less than 3, that's these numbers left of 3. And yet again, just like examples 1 through 9, if numbers are showing up on this rough graph, they are solutions of these OR inequalities, right? Any number that satisfies either inequality is satisfying, is making the entire compound inequality true. So there's a description of the solutions. My final graph looks like this. 3 and 12 are here, and all the numbers less than 3 but not 3. All the numbers greater than 12 but not 12 are solutions of the compound inequality. And then again, 2 intervals with a gap between them, just like examples 1 through 9. So first interval, going from left to right, you got negative infinity up to 3, and parentheses on those, because again, 3 is not a solution. Union for the gap, right? Union for the OR. And then from 12 to infinity, parentheses on those, right? Because again, 12 is not a solution. Okay, so first 10 examples have all been very similar. Well, I'm hoping that one of these last 4 gives us a little bit of a different result, and we'll see. Here I'm going to be adding 2, giving me 6 on the right. Dividing by 3 would give me 2 on the right. And again, I didn't multiply or divide by a negative. So x is greater than 2, those numbers satisfy the first inequality. Or here I'm adding 3, getting 10 on the right. Then divide by 5, I get 2 on the right. X is less than or equal to 2. Okay, so here's going to be a different kind of result. Because both, so far all the previous examples, 1 through 10, the numbers that came up in each inequality were different. Here they are the same. So in my rough sketch over here, the only number that shows up in either of these is 2. Now, x is greater than 2 are these numbers. X is less than or equal to 2 are these numbers. So if you put those together, that's every single number, right? All the numbers less than 2 are going to be considered solutions of the compound inequality because they satisfy the second inequality. 2 itself is a solution because it satisfies the second inequality, and everything greater than 2 is a solution because it satisfies the first inequality. So what I'm seeing here is that every real number is a solution of this compound inequality. Okay, so instead of writing it like this, all right, I'm not going to circle this. This is what I'll circle. X can be anything. I can replace x with any number I want, and one of these will be satisfied, at least one of them. All right, so the whole thing will be considered true, right? One of these or statements. So then for the graph, it's just everything. Every single number. I indicate every number on the real number line, all the way to the left, all the way to the right. No gaps this time, right? There's no breaks like in examples 1 through 10. So then for the interval notation, and you've probably seen this in other videos, right? For the entire real number line, right? This is there's no gaps in it, so it's a single interval. Left to right, I'm going from negative infinity to positive infinity, right? And parentheses always on the infinities, right? So here's the graph, and the interval notation is this negative infinity to positive infinity with parentheses around it. That indicates you're talking about the entire real number line. Every single number is a solution of this compound inequality. So finally we got an example that ended up being a little different than examples 1 through 10. Right. And who knows, perhaps these next few will be something similar. Example 12. So again, I'll solve these. Now this one I divide by 2 and then subtract 3. We'd have x is greater than or equal to negative 3. Or here I'm dividing by 3, giving me 2 on the right side, and then subtracting 4. Now 2 minus 4 is negative 2. We have x is less than or equal to negative 2. And again, I'll draw a rough sketch over here, a rough graph. Now the numbers mentioned are negative 3 and negative 2. Sure, they're different, but look at these graphs. All right, watch these graphs. X is greater than or equal to negative 3. That's these numbers. On top there. X is less than or equal to negative 2. That's these numbers that I put on the bottom. And again, just like in the last example, this picture, because it's an or statement, right? We're looking for numbers that satisfy the first inequality, the second inequality, or both. At least one. Well, look, all the numbers to the left of negative 3 satisfy the second one. All the numbers between negative 3 and 2 satisfy both. and all the numbers to the right of negative 2 satisfy the first one. So again, looking at this picture, instead of circling this, I'm going to say, hey, all real numbers, every real number is a solution of this compound inequality. So all real numbers are solutions. You could pick any number you wanted. Replace it with x. Right? Replace x with any number you wish. And at least one of these will be true. This, or both. Right? So that or statement will be satisfied. Okay. And then just as before, the graph is, everything. I just indicate that everything is a solution. All the way left, all the way right, and then the interval notation, same as before. This interval is one big piece going from negative infinity to positive infinity. Again, parentheses always on the infinities. Right? So there's the graph and your interval notation. But yet again, I have an example where every single number I could pick satisfies the OR statement, satisfies the compound inequality. All right. Next one. Here I would add 3 and then multiply by 2. So give me 7, then times 2 is 14. X is less than or equal to 14 for the first inequality. Or, and this one I'd multiply by 3, giving me negative 6. Then adding 6 would give me 0 here, and I wouldn't change the inequality symbol since I never multiply or divide by a negative number. And here we go, we have x is less than or equal to 14, or x is greater than or equal to 0. And again, in my final solution, my final graph, I want to draw a picture of all the numbers that satisfy either one of these or both. I'll make a rough sketch again. 0 and 14 are mentioned. X is less than or equal to 14, that's these numbers. X is greater than or equal to 0, it's these numbers. And every single number I just drew satisfies at least one of these, so it satisfies the compound inequality. So look, just like the previous example, the previous two, every real number works. All the numbers to the left of 0 satisfy the first inequality. All the numbers from 0 to 14 satisfy both. And all the numbers to the right of 14 satisfy the second inequality. Every single number on the number line satisfies at least one of these, so it satisfies the entire compound statement. So yet again, all real numbers are solutions. Let's circle that. Right? And then same graph, same interval notation as example 12 and example 11. I just indicate, hey, everything is, no matter what I pick for x, this compound statement is going to be true. And then this is one big piece, so one big interval from far left to right here, negative infinity to positive infinity, and always parentheses on the infinities. And there's your graph and interval notation for that graph. Right. Wonderful. And I've got one last example, the last exercise from section 2.6 on this stuff in the intermediate algebra second edition from openstacks.org. So same stuff. I need to solve these things. First, here I would subtract 2. It gives me negative 3 on the right side. Then I'd multiply by 4/3. Negative 3 times 4/3 would be negative 4. X is less than or equal to negative 4. And again, it's still less than or equal to because I never multiplied or divided by a negative number. Or, this one, to get rid of the half, I'd multiply by 2. That'd make this negative 6. And then subtract 8 to get x alone. Negative 6 minus 8 is negative 14. And it's still greater than or equal to, since I never multiplied or divided by a negative number, it wouldn't flip the symbol. Here's a rough graph. Again, the numbers mentioned here after solving are -4 and -14. Now be careful with negatives. I've said this before. Right, -14 would be to the left of -4. Now all the numbers less than or equal to -4, that's these numbers I'll put up top here. All the numbers greater than or equal to -14, that's these numbers, and yet again you can see that every number you can think of, every number on the real number line satisfies at least one of these. Every single number you think of is on one of these pieces of the graph. Right? All the numbers less than -14 satisfy the first inequality. All the numbers from -14 to -4 satisfy both, and all the numbers to the right greater than -4 satisfy the second inequality. So every number on the number line, again, is a solution of this OR statement, a solution of this compound inequality. So one more time here, I'm going to write all real numbers are solutions. Right, no matter what you choose for x, it's going to satisfy this statement. And same graph, same interval as the previous three examples. Just indicate, hey, everything, far left, far, everything's a solution. Interval from negative infinity to positive infinity, and parentheses on those. Yep. Wonderful. Okay, so hopefully watching me go over these helps you out when you're working on similar problems in some other textbook. And thank you very much for watching.